Good morning. My name is Fabio Cuzzolin. I'm a professor of artificial intelligence at Oxford University in the UK. I'd like to thank the organizers for inviting me to speak at this excellent DeepView 2021 workshop. And today I'd like to tell you about a road project for the creation of a road event awareness dataset for autonomous driving. So the problem that we wanted to address with this dataset is situational awareness in autonomous driving. Cars, as you know, need to be aware what happens in their vicinity, and that means they need to understand what events are taking place, the behavior of other road agents, such as pedestrians and bicycles, and so on. The final goal, however, is to be able to provide the decision-making core with enough information to plan a course of actions, as you can see in this picture here. So the autonomous car is supposed to survey the environment using one or more sensors, including cameras, understand what happens in the environment, for instance, that these people are crossing the road here, and then make a decision about the best course of action. In particular, we were interested in vision-based situational awareness. As you know, the latest generation of RobotCar is equipped with a range of different sensors, including laser, radar cameras, and GPS. And the information is then extracted and fused to suggest how the vehicle should move. However, some authors maintain that vision is sufficient, is a sufficient sense for autonomous vehicles to navigate their environment, supported by their ability, the ability of humans to just do so. This is what is called vision-based autonomous driving. For instance, people are just able to drive simply using their vision sense. The question is, what do we instruct to this visual information? Object detectors, which are very popular in computer vision, only allow us to see what's out there, but not to really understand it. Whereas we need to look towards vision-based semantic perception, so we need to understand the behavior of other road users from video sequences captured by the cameras mounted on the vehicle in a streaming online fashion. So there's mainly two different views on decision-making for autonomous driving. There's a popular approach which consists in end-to-end reinforcement learning from raw video data, where the behavior of a human driver in response to road situations is used to train in an imitation learning setting an autonomous car to respond in a more human-like manner. This, however, requires an astonishing amount of data from a myriad of road situations. For instance, Friedman et al. Showed that for highway driving only, they had to use a whole fleet of vehicles to collect 45 million frames. And other authors have recently highlighted the insufficiency of models that directly map observations to actions. Our stance is different. Our stance is that most appearance information is completely relevant to decision making. So we don't really care, for instance, what color a vehicle is in order to avoid it. So what it makes sense, more sense to do in our view, is to extract from road scenes semantically meaningful concepts as a stepping stone for intention prediction and automated decision making. So in terms of data, we considered a number of options, and we ended up selecting this Oxford RobotCar Dataset produced by the Oxford University Robotics Institute back in 2015. And it contains 100 repetitions of consistent route through Oxford, UK, captured over a period of a year using this autonomous Nissan Leaf vehicle. It includes the different combinations of weather, traffic conditions, and presence of pedestrians, along with longer-term changes such as construction and roadworks. So the Oxford RobotCar dataset contains quite a lot of data, actually, and it's a very good dataset, including data types for object detection, dense 3D reconstruction. You can see some examples here on the right, point clouds. What's missing, however, is event understanding, which is what I was talking about. So any annotation that allows us to test the ability of the vehicle to recognize the meaning of what's happening in the road scene. So the very top of the perception layer cannot really be tested using the RobotCar dataset. For instance, action detection approaches which to date are completely supervised with annotation in terms of bounding boxes cannot be tested. So based on our expertise on online action detection, we decided to create such a test bed, and we call it ROAD, Road Event Awareness for Autonomous Driving Dataset. The dataset is designed to contain both atomic events, for instance, car turning left, car indicating, and as well as complex activities, for instance, a number of cars negotiating an intersection. So let's see what the features of this road dataset are. Again, ROAD stands for Road Event Awareness Dataset for autonomous driving, and it's the world first benchmark dataset of that kind, at least as far as we understand. We created that by annotating a number of videos from the existing Oxford RobotCar dataset. In particular, we annotated 22 videos, almost all of them 8-minute long, for a total of 122,000 annotated frames. The important feature, the most important feature of ROAD is that it's a multi-label data set. So there's 3 types of labels: agent labels with 11 classes, action labels with 23 classes, and initial and final location as well with 13 classes. So you can see here an example of an annotated frame on the right. So this is annotated as medium-sized vehicle, this is annotated as car, this is cyclist, but actually each bounding box has 3 different types of labels, as I explained. So agent, the action it performs, and the location with respect to the autonomous vehicle that is perceiving the scene. And the aim is to have use this as a benchmark data set to test prediction capabilities, event detection, but also complex, the detection of complex road activities. I will explain that a little bit later. We have a PIE paper under major revision on this data set, and we organized this road at ICCD 2021 workshop and challenge in mid-October, which was resting entirely on road data set. I'll tell you a little bit more about that later. So how did we annotate all these video frames? So 122,000 video frames. We use a tool produced by Microsoft called the Virtual Object Tagging tool. And this is the GitHub link for the tool. We consider again a number of options, including MATLAB toolboxes, but we decided this was the easiest, also supervisor ally. We decided this was the easiest tool to use because it allows us to easily draw detections and also click on as many labels as necessary from a list, as you can see here. And the important feature, the most important feature possibly, is that detections are automatically linked in time to create ground truth tubes. So the benchmark is for video level detection. So we don't expect algorithms to detect object or events only frame by frame, but to detect them at video level. And that means that road events and even object agents are represented as series of bounding boxes linked over time, so in the form of tubes. They can be action tubes if the label is action, or agent tubes if the label is agent, or even event tubes, as I will explain. There were 2 teams of annotators, one in Oxford Brookes University, UK, and one in Mazandaran University, Iran. So this is a multi-label, multi-instance data set specifically designed for the perspective of self-driving cars. There were 3 different types of labels for each road event, as I just explained. The category of the road user relative to the autonomous vehicle perceiving the scene. So for instance, cyclists, the location of the road user. So in ongoing lane, in incoming lane, on the pavement. The category of road user involved, so pedestrians, small vehicle, large vehicle, cyclist, and also, crucially, the type of action being performed by the road user, for instance, moving away, moving towards, crossing the road. Again, all these descriptions are from the point of view of the autonomous vehicle that is perceiving the scene. Multiple agents might be present at any given time and perform multiple actions simultaneously. Each agent can perform more than one action at each time. So for instance, a car can be turning right and indicating right simultaneously, as I said. The most important contribution of this work is the definition of what a road event is. So by road event, we mean a triplet, agent, action, location. So that is what we consider to be a road event. So complete description of what a specific road agent does and where it does it with respect to the ego vehicle perceiving the scene, as I said. So in addition, each video frame is also labeled with the action performed by the autonomous vehicle itself, for instance, moving, stopping, overtaking, and so on. That is designed to test the decision-making capabilities of the algorithms. So the principles are that event awareness is crucial to determine the course of action of the AV. And the dataset was designed according to these objectives. It's supposed to be a multi-label benchmark in which each road event is composed by the label of the moving agent responsible, the labels of the type of actions being performed, and labels describing where the action is located. The labeling is done from the point of view of the autonomous vehicle, because the final goal, as I said, is for the autonomous vehicle to use this information to make the appropriate decisions. And each event can be assigned multiple instances of the same label type whenever relevant. For instance, a road event can be an instance of both action classes moving away and turning left, because a car can be moving away and turn left at the same time. And also the metadata is intended to contain all the relevant information to fully describe a road scenario. So basically the idea is that you could close your eyes and just by having the list of labels in your head, you could picture out the scenario in your own head. Or equivalent, this is sufficient information for the AV to be able to make an informed decision. This is a little diagram that represents this concept. So how do you describe scenarios in the road semantics? So for instance, on the left, you have the autonomous vehicle. There's a vehicle in front of it that is turning left or changing lane. So, so the green car in front of the AV changes lane as depicted by the road arrow. The associated event will then carry the following labels. In vehicle lane, which is the vehicle where the autonomous vehicle is, which the autonomous vehicle is using, moving left. Once the action is completed, the location label changes to in outgoing lane. Okay. On the right, you have another example. So you have the autonomous vehicle turning left from lane 6 into lane 4. Lane 4 will be the outgoing lane as the traffic is moving in the same direction as the AV. However, if the autonomous vehicle turns right from lane 6 to lane 4, so makes a wrong turn, lane 4 will become the incoming lane. So again, the labels and the combination of different combinations of labels are designed to provide a complete full representation of the scene from the point of view, not from the bird's eye view, but from the point of view of the autonomous vehicle that needs to make a decision. This is a list of agent labels in roads. So as you can see, there's, I think, 11 or 12 agent labels. For instance, autonomous vehicle itself, car up to the size of a multi-purpose vehicle, small vehicle, medium vehicle, large vehicle. We created a taxonomy for different labels by carefully analyzing the videos in the Oxford RobotCar Dataset. So the descriptions that you can see here guided us through the annotation process in order to make the decision consistent across different annotators, and also for them to have a semantically meaningful interpretation. For instance, an emergency vehicle is an ambulance, a police car, fire engine, indicated by red and blue flashing lights. We have also a list of action labels, I believe 23. For instance, you have moving away, agent moving in a direction that increases the distance between the agent and the AV. Moving towards, the agent is moving in a direction that decreases the distance between the agent and the AV. Moving, the AV is in motion. Reveering, the agent is moving backwards, most likely a vehicle. Stop, the agent is stationary, indicating left or right using the flashing indicator light. Hazard lights on, hazard lights are flashing on the vehicle, for instance, an emergency vehicle. You have crossing road from left, for instance, agent crossing road, starting from the left pavement and moving towards right pavement, and you have the opposite action, crossing road from right. Pushing object, sometimes pedestrians pull a trolley or a push chair, a wheelchair or a bicycle. And we also have a number of actions for traffic lights because these are relevant to the decision-making process of the autonomous vehicle. For instance, we have traffic light red, amber, or green, and the car, the AV, needs to respond will make decisions depending on the configuration of the traffic light. We also have location labels. Actually, as I said, they're from the point of view of the AV. For instance, in vehicle lane means the agent is in the same road lane as the AV. In outgoing lane means that the agent in a road lane that should be flowing the same direction as the vehicle lane. And in outgoing bus lane means that the agent is the bus lane that should be flowing the same direction with the AV, and so on and so forth. For instance, on left pavement to the left side of the AV. On right pavement to the right side of the AV. On pavement means a pavement that is perpendicular to the movement of the AV. So all these labels and their description have been carefully designed after visual inspection for a prolonged period of time of the readers in the Oxford RobotCar Dataset. These are some frames with sample annotations. Unfortunately, the labels are a bit small, but you can see there is a medium vehicle, large vehicle, car, pedestrian. These are only agent labels, but like I said, each bounding box, each individual bounding box and each tube carries three different types of labels. And actually for each of the three different types of labels, there can be more than one instance attributed to that bounding box or that tube. So like I said, a car can be turning left and indicating left at the same time. They can be moving away and indicating or having flashing lights on. So it's a multi-label dataset in many different levels. The little box over here you can see is the action associated with the autonomous vehicle itself, which we marked with a small bounding box at the bottom. Here you have other sample annotated videos with all the three labels. Again, they're a bit small, but if you want to know more about this, you can check out the road at ICTV'21 workshop website that we organized on October 16, 2021. This is the website for you. And here you can also see a few examples. These are invited speakers. Here you can see a few examples of running videos. So it's quite a rich data set. As you can see here, the annotation is quite rich. It's time consistent and it's multi-label in nature. So the quantitative summary of the raw data set is as follows. There are 22 videos, each 8 minutes and 20 seconds long. It includes 170 minutes of video content in total. So overall, there are 122,000 frames. They started from 22 videos, labeled at around 12 frames per second. So all videos are 8 minutes and 20 seconds long, except 3 whose duration is 6 minutes 34, 4 minutes and 1 minute 37. In total, there are 560,000 bounding boxes with 1.7 million instances of individual labels, broken down as written here. Around the same numbers of 500,000 labels for agents, 500,000 labels, 600,000 for actions, and 500,000 labels for locations. Those bounding boxes, they make up 7,000 tubes for agent tubes, almost 10,000 action tubes, 8,000 location tubes, 9,000 agent action combination or duplex tubes, and 8,394 tubes that correspond to road events as defined before. So triplets, agent, action, location. So this is a little analysis of the class imbalance problem on road, as you can see, and also as it's quite familiar. If you're familiar with autonomous driving data sets, you will know they all suffer from class imbalance because some road events and some road agents are just more frequent than others, so they appear more often in videos. Some other actions and events are very rare, so they appear very few times, and that's also the case in road. So this is the list of labels for autonomous vehicle actions, road agents, and actions, I think, but also locations, some of them, not all of them. So you can see there's a lot of disparity between things like, object like pedestrians, they appear an awful lot of times, whereas other objects like emergency vehicles, agents, they don't appear that often, so like 500 times as opposed to 200,000 times. In terms of actions, you have actions that like stopping that appear like, again, more than 100,000 times, and others like overtaking only appear like maybe 1,000 times. And this disparity is even worse at video level, and, as indicated in blue, for instance, emission vehicles at video levels appear very, very, very seldom. For instance, here you have maybe 7 or 8 tubes, complete tubes for emergency vehicles, whereas you have 5 or 6,000 tubes for pedestrians. So there's a huge class imbalance problem. Brief comparison with other data sets like KITI or Cityscapes or Mapillary or BDD 100,000. Number of frames, okay, this is not up to date. Again, number of images 122,000, completely annotated. So it's comparable, say, with Apolloscape, and it's bigger than others. BDD 100K is like, yes, 120 million images, but the actual annotated images, number of annotated images in terms of semantic segmentation is only 10,000. So it's not a small, it's a medium scale data set, I would say, but the main feature is the richness of the annotation. Since the raw data set is specifically designed to test event and action recognition and detection, the richness of the annotation is much bigger than that of other data sets that have been proposed for autonomous driving before. And also it's very challenging in nature because of the weather conditions that we consider: snow, rain, night, reflections, partial observability, as you've seen in the few examples of video frames that I showed before. So what can you use road for? You can set out a number of tasks. This is what we did. So road can be used to allow manifold tasks associated with situation awareness or self-driving. Each of these tasks is associated with a label type or a combination of 2 or 3 label types. And namely, you can have spatial all these tasks have spatial temporal, So we're not testing frame level detection, we're testing video level detection at the level of action tubes. You can do agent detection, you can do action detection, location detection, agent action, so the combination of these 2 labels. Road event detection as defined by the triplet agent, action, location, as well as temporal segmentation of AV actions themselves. Since the data set is multi-label by construction, separate analysis can be conducted by considering different combination of labels. And this is what we're doing in our PIE paper under major revision at this point. So for instance, pedestrian moving towards the AV on the right pavement, or cyclist overtaking the vehicle lane are the result of combining agent, action, and location labels. This is what we mean by a road event, really. Note that not all those combinations make sense. So some combinations will elicit the same response on the AV, the decision-making core of the autonomous vehicle. And so they should be considered as equivalent from a semantic point of view. Among all those tasks, we selected 3 for our road challenge at ICCB. So next, I'll present the ICCB challenge based on road and the baselines for that. So like I said, all these challenges are video level. So spatial temporal detection tasks, you need to produce tubes, agent tubes, action tubes, or event tubes. Yes, instances need to be localized in both space and time. So challenge 1 was action detection, in which the output is in the form of agent tubes collecting the bounded boxes associated with an inactive road agent in consecutive frames. Like I said, in an object tube formulation. Challenge 2 was action detection, so output in the form of action tubes. Challenge 3 was road event detection, where by road event, like I said over and over, we mean the triplet, agent, action, location, and each road event is once again represented as a tube of frame level detections. As the autonomous vehicle decision make use of all these 3 types of information, all these tasks are very significant for autonomous driving applications, especially the last one, so challenge 3. Evaluation was done in terms of video, mean average precision of video MAP as standard in action detection. We also proposed a baseline, which is also described in our PIE paper. We call the baseline 3D RetinaNet, which is inspired by feature pyramid network. It's basically an inflated version of RetinaNet using a ResNet feedback backbone. So it inflates the 2D backbone into a 3D one in a nice 3D fashion. If you're familiar with inflated 3D CNNs, you know what I'm talking about. And then there's a pyramid, feature pyramid representation, and finally some branches that do the bounding box regression and the class regression, class estimation. There's also a separate branch, the bottom branch over here is the one that recognizes the ego actions of the autonomous vehicle. We measure the performance of 3D RetinaNet on UCF 101-24 as the standard benchmark for action detection at both at frame MAP and video MAP at different IOU thresholds. So frame MAP was measured at intersection over union 50% between the predicting bounding box and the ground truth bounding box. And video level MAP was measured different IOU thresholds, 0.2, 0.5, 0.75, and the interval 0.5 to 0.9. And as you can see here, after comparison with a number of state-of-the-art approaches, you can see that 3D RetinaNet is quite competitive with the current state-of-the-art, even though several of those methods they use both RGB and optical flow, whereas 3D RetinaNet only uses RGB appearance. You can see in bold here that the performance of 3D RetinaNet in the inflated version is quite competitive with what the state-of-the-art is. Although, like I said, we're not using flow as input stream. A strong baseline method, which retains the simplicity of single-stage methods, and it's described on the GitHub repository over here. So please take a look at GitHub repositories for both the dataset and the baseline. For the challenge, we divided the 22 videos into training, validation, and test falls. So challenge participants had 18 videos available for training and validation. The remaining 4 videos were used for testing, for testing the final performance of their model. And the same split was applied to all the 3 challenges. In the PIE paper, we actually described 3 different splits, which are designed to assess performance after different weather conditions, for instance, night, rain, and snow. But for the challenges, we only selected split 3. So here, the first figure here is the number of training videos. The second figure is the number of validation videos. So in split 3, you have 4 sunny videos and 3 for training and 3 for validation. You have 7 overcast videos for training, but none for validation. And same for snow and night, you have 1 snowy video for training and 3 night videos for training, but none of them are present at validation in the validation form. So that makes it quite challenging. And you have an even spread of test videos over the 4 weather conditions, 1 for sunny, 1 for overcast, 1 for snow, 1 for night. So for the challenge, we had participant validated models only on split 3. The timeline of the challenge was as follows. So challenge opened for registration April the 1st, 21. Training validation data was released on April the 30th, 21. Test data was released on July the 20th. The deadline for submission of the results was supposed to be August the 10th, was extended to September 25th. And we announced the results at the end of September. The workshop took place on October 16th. Like I said, the dataset is available on GitHub here. So please go and check. It says complete description of the data set, how to download it. All the scripts are ready for loading the data and storing them on folders. The annotation structure described, and also the type of annotation. And here you can see also there's a link to the 3D RetinaNet repository for the baselines, all the code. Okay. So please take a look. 4 test videos can be downloaded directly from Google Drive by following this link. Baseline results of 3D RetinaNet were as follows. So they were tested at 3 different IOU intersection over union thresholds, 0.1, 0.2, and 0.5. So for agent detection, we got an MAP at 0.1 of 34, which would degrade to 12.15 to 0.5, another 25. Event detection, as you can see, which is about detecting this triplet agent action location, was more challenging with the MAP at 0.1 and 23, degrading to just 6 at 50% overlap. So you can see how challenging the data set is as a benchmark for agent detection, action detection, or event detection. Much more challenging than existing benchmarks for action detection, for instance, so like UCF101, GHMDB, or even AVA. So ROAD is a significant step forward in terms of the level of challenge for action detection. So we hope the action detection community in computer vision will take this up as a challenge. Evaluation took place on the eval.ai platform. This is the link for the challenges, so with the own description of the challenge and also the leaderboards. You select a phase over here, you can see the leaderboards for validation and so on. For each stage and each task, the maximum number of submissions was capped at 50 with the additional constraint of 5 submissions per day to make the challenge fair. The results after different weather conditions are as follows. So these are taken from the PIE papers. So for the different splits, you can see the split one, in which all the 3 validation videos were taken at night and no time videos are used for training as the lowest validation results. So this is split 2. You can see the numbers here are much lower, much lower. Split 1 has 3 overcast videos in the validation set, but also 4 overcast videos in the training set. The resulting network has the best performance across the 3 validation splits. The results seem to attest a certain degree of robustness of the baseline to weather conditions. But again, there's more information on the PIE paper and the archive version of it. What were the results of the challenge, the ROAD ICV'21 challenge? So the winner of the agent detection challenge was this team. The team name was JWHSS. This is the name of the people: Chen Chengwing Li, He Chen, Xu Han Wang, Fang Zhanghua, and Fang Lu. You can see here their action detection performance was much better than the baseline, so 58.29 compared to 34 on the baseline. At 50% overlap, the agent detection performance MAP was 32 compared to 12 on the baseline, so significant, very significant improvement. Their method was based on YOLO v5 with post-processing and a number of different additions to YOLO v5. Again, this table summarizes the agent detection challenge. You can see the marked improvement in performance from the baseline to the RetinaNet to the winner of the agent detection challenge, YOLO v5 with post-processing. So agents are linked by evaluating their similarity between frames and grouping them into a tube. And this is what these guys have done. This continuous tube was completely used through frame filling using more motion information. And YOLO v5 also generates some ground bounding boxes that do not have the right agents, but these bounding boxes are scattered in different frames. So the team would take advantage of this feature to filter out incorrect bounding boxes by filtering out the shorter tubes. The action detection challenge was won by the CMU INF team with a contribution called Argus Road Activity Detection with Connectionist Spatial Temporal Proposal. Here, the improvement from the baseline was less marked, but still significant. So from 2550 to 2854 for agent, for action at 0.1%, 10%. 20% overlap from 1940 to 2563, and at 50% overlap, the increase wasn't so good. But overall, so other teams had better improvement at 50% overlap, as you can see here. So these are the authors, members of the team, the Argus Road team. This is based on the Argus++ framework that was designed for real-time activity recognition extended videos for the NIST active challenge activities in extended videos challenge. This is the website for the challenge. And it's the best performing system since fall 2020. This is a block diagram of the approach. Some adaptations were needed for road, for instance, video MAP instead of frame MAP, and also 3D IOU measures spatial temporal alignment of tubes, needing a precise bounding box in each frame that the original framer wasn't providing. The leaderboard is the leaderboard for the event detection challenge, which was the main challenge at the workshop. You can see here the winning team was IFLY by Huiji Hu and Fengyang Wang from the University of Science and Technology China and IFLY Tech. Their improvement from the baseline was quite significant too, from 1650 to 20.86 in average. Especially at 10% of the lab, the improvement was around 5 percentage point, reducing to 3 percentage point at 50% of the lab. They made a number of amendments to the 3D RetinaNet baseline, so their approach was based on 3D RetinaNet with a number of amendments, including bounding box interpolation, better tuning of the optimizer. They analyzed both edge stochastic gradient descent as well as ADAM, different types of different batch sizes, and improved feature extraction with a combination of RCN, GRU, and LSTMs, smooth L1 loss function, and also data augmentation. The best results they obtained using an ensemble model. So these are the numbers. The ensemble model had, I think, all these 3 feature extractors combined. We are planning to write a summary paper for the challenge. It's probably a journal paper, so we'll invite all the contributors from the top teams to contribute to the paper and describe their methods in more detail. Some challenge statistics. Total in the test phase, we got 138 submissions for the agent detection challenges with 9 participant teams, 98 submissions for the action detection one with 8 participant teams, and 93 submissions for the event detection challenge with 6 participant teams. This improvement from the validation phase to the test phase is due to us extending the deadline from mid-August, where a lot of people were on holiday, to end of September, where a lot of people were actually there, interested in participating in the various challenges. So all in all, the challenge was a success, we believe. I'd like to conclude with a little discussion of the ongoing extension. So ROAD is an open project. It doesn't end with the challenge. It doesn't end with the Oxford RobotCar Dataset. We plan to extend the project to more datasets. We plan to extend it in terms of different types of annotation and different types of baseline for different tasks, such as intention and so on. So I'm going to describe them quite briefly in the next few slides. Some of these extensions are already ongoing. So we want to collect data from more cities in different countries, off-road routes. And right now we are working on extension to the PIE, the pedestrian intention estimation dataset, and the Waymo datasets. And also, thanks to our collaborator of ours, we are also working on testing the baseline on Indian road videos. We are planning to generate, we have a project in my lab on machine theory in mind, which is about guessing the reasoning process of other agents, including road agents. So we are planning to extend the annotation to provide theory of mind annotations of the data set. So the mental states of the agents, the drivers and the cyclists and the pedestrians on the route. Another ongoing work, which is under review at AAAI-22, is Road R, so Road with Requirements, where we provide common sense constraints for the neural predictions of the baseline to obey. We have extended the annotation to include complex road activities, for instance, cars negotiating intersection, cars waiting in a queue. We are working to make road a benchmark for intent prediction as well, of both cars and pedestrians. And we want to make it, propose it as a benchmark data set for continual learning as well, because of the long duration nature of the road videos, which are more than 8 minutes long. So like I said, we are working towards this Road++, which is an extension of road-like annotation to Waymo and the PIE dataset. These are important datasets in autonomous driving. PIE, Waymo. In Waymo, object tubes are already given for 3 classes: pedestrian, vehicle, and cyclist. So we just need to relabel all these tubes according to our taxonomy. And we also need to create new tubes for traffic lights, which were not present in the original Waymo annotation. PIE, the pedestrian intention dataset, is possibly the closest to road, and so it's a natural candidate for an extension of road, like road event annotation. We actually are working on that. The goal is to propose this road multi-dataset benchmark and challenge the community, and challenge the community at ICCV 2022, and possibly using via paper. We're going to submit one or more papers. We're going to submit to ICCV 2022. Like I said, we're also thinking of providing machine theory and mind predictions, so not just so predictions in the annotation in the form of the estimated chain of reasoning of road agents, for instance, in the form of theory and mind simulations of what the agent cyclist is thinking at this time when he turns left. I actually made this the topic of my professorial talk when I was promoted to full professor a few years ago. You can actually still consult it on Facebook. So please do that if you're interested in working at interface of AI and neuroscience. Can we, the research question is, can we predict future behavior using this machine theory mind concept? So can we guess both future behavior and also explain the chain of reasoning behind this future behavior? We have an editorial in Psychological Medicine from 2020 on this topic. We have a AAAI 2022 paper pending, like I said, on road R, learning with requirements, in which we augmented road with common sense requirements pertaining to individual agents. And the idea here is to assess how often neural network predictions violate common sense requirements. For instance, a traffic light cannot be red and green at the same time. So as part of this paper, this paper proposes this augmentation of road that we call road R. In road R, the requirements express the condition on the set of admissible road events and are formulated as logical constraints. And in the paper, we show that even current state-of-the-art models produce an awful lot of non-admissible predictions. So predictions that are illogical, and neural networks just by themselves are not able to realize that. We do propose two baseline methods for computing a minimal set of corrections in order to fix that problem. We provided additional notation for complex road activities. For instance, activities, by complex road activities, we mean activities performed by multiple agents over a period of time. For instance, number of cyclists or number of vehicles, negotiating intersection or waiting in the queue. We looked at the videos, we created a list of 6 classes of complex activities, and we published at the AVSS'21 a graph-based method for detecting complex road activities, in which every action tube in the scene is arranged into a graph, and then we apply convolutional graph networks to extract the feature representation and classify graphs of road scenes from snippets. We are extending this annotation to Waymo and PIE as well, and we are working to extend this framework too. Finally, we want to propose road as a continual learning benchmark, because the next step for us is continual road scene understanding instead of offline road scene understanding. Continual learning means the ability to keep learning from a continuous stream of data, either supervised or unsupervised. Almost no realistic computer vision data sets exist with this, except maybe Core 50 on object detection produced by Lamonaco and co-author. And whereas low lend itself well as a continual supervised learning benchmark, videos are long, 8 minutes, unlike in ActivityNet or Tumors or many other data sets, which only contain snippets. And they are rich in annotation in terms of both labels and boundary boxes. In our team, we recently actually released a continual activity recognition dataset as part of the continual semi-supervised learning workshop at ICCAI 2021. So please, you're invited to check out the website for this other event as well. And we are currently working to make road into a continual learning benchmark together with the Continual AI Society. Thanks very much for your attention. Again, thanks for inviting me. That would conclude my presentation.